Have you ever wondered how your phone just knows how to track your face for a filter, or how a self-driving car can see a person about to step into the street? Well, it all comes down to one single crucial skill: understanding motion. So today, we're going to pull back the curtain and break down exactly how computers learn to see movement.
First, we'll start with the basic illusion of motion itself. Then we'll look at how computers spot what's changed between two moments. After that, we'll get into the clever math they use to actually track that movement. We'll explore why this is so important for everything from your Netflix binge to self-driving cars. And finally, we'll get a peek into the tough engineering choices that make it all work.
All right, let's kick things off with the illusion of motion, because before we can understand how a machine sees movement, we have to talk about what a video really is, and the answer might surprise you. So here's the fundamental trick. A video isn't actually a moving picture at all. It's an illusion. You know, just like one of those old-school flipbooks you made as a kid? It's just a rapid-fire sequence of still images we call frames. And when you flash those frames in front of our eyes, usually at about 24 to 60 frames every single second, our brains get tricked into seeing smooth, continuous motion. And each of those still images is called a frame. Now think about it this way. A normal photo has two dimensions, right? Height and width. But a video adds a third, an absolutely crucial dimension: time. And it's by looking at the changes across that dimension of time that a computer can even begin to understand what motion is. Okay, so if a video is really just a big stack of still photos, how in the world does a computer figure out what's changed from one photo to the next? This is really the first big puzzle to solve. So imagine a computer is looking at this single frame of a highway. For the computer, this isn't a highway. It's just a grid of colored pixels. At this one specific moment in time, nothing is happening. It's completely static. Then, just a fraction of a second later, boom, it sees this next frame. Now, to you and me, it's totally obvious the cars have moved forward. But how does the computer know that? How does it actually quantify that change? Well, this is where a really simple but brilliant idea comes into play. The computer literally subtracts the first frame from the second one, pixel by pixel. Anything that stayed the same, the road, the sky, the mountains in the back, it all cancels out and just turns black. So what's left behind? Only the pixels that moved. This is motion detection in its most basic form. But, and this is a huge but, there's a big catch. This method tells us that something moved, and that's it. We're just left with these white blobs. We have no idea which way they're going or how fast. So to get that kind of useful information, we need a much smarter approach. And to solve that problem, we need a way more sophisticated tool. This brings us to the whole idea of motion vectors. This is how we go from just seeing change to truly tracking it. This whole process is called motion estimation, and the goal here is to create something called motion vectors, which you can just think of as little arrows that tell us exactly where a piece of the picture moved from one frame to the next. So how does it actually make those little arrows? Well, a really popular way is a technique called block matching. So imagine the computer takes a small square of pixels in the first frame. See the one around our snowboarder? Then, in the very next frame, it searches around in a small area trying to find where that exact square of pixels moved to. It's kind of like a tiny game of Where's Waldo being played thousands of times every single second. And the result of that little search is the motion vector. It's a really simple but powerful piece of data. It's just a pair of coordinates, something like 5, 3, that basically says, hey, that block of pixels moved 5 pixels to the right and 3 pixels down. Now do that for thousands of blocks all over the image, and suddenly you have a super detailed map of all the movement happening in the scene. Okay, so all of this is pretty cool from a technical standpoint, but why should you actually care? Well, it turns out this technology is quietly running the world all around you, from the shows you stream to the cars we'll be driving in the future. The biggest and most widespread use is video compression. You see, raw video files are absolutely gigantic. We're talking gigabytes of data for just a single minute. So video formats like the ones Netflix and YouTube use, they use these motion vectors to be incredibly efficient. Instead of sending every single pixel of every frame, they send one full frame, and then for the next few frames, they just send the motion vectors and a few little corrections. That is the secret sauce that lets you stream video without completely destroying your internet connection. I mean, just look at this. It makes perfect sense, right? The background here is completely still from one frame to the next, so why on earth would you waste bandwidth sending that same exact information over and over again? It's so much more efficient to just send the data that describes how the person moved. Next up, we've got object tracking. See, once you have these motion vectors, you can logically follow an object from one frame to the next. This is the absolute backbone of modern surveillance systems. It's how sports analysts can track every move a single player makes, and it's how smart cities can monitor traffic flow in real time.
And this one is absolutely huge: autonomous driving. For a self-driving car to be safe, it must understand motion, period. It uses these exact principles to predict where a pedestrian is about to walk and to keep track of every other car on the road. Understanding motion isn't just some cool feature. It's the foundation that the entire system is built on.
But that block matching thing we talked about, it's not quite as simple as it sounds. It actually creates a really tough puzzle for engineers, a constant balancing act between two things you always want: speed and accuracy.
So, on one hand, you have what's called an exhaustive search. This method is slow, but it's perfect. It literally checks every single possible location to find the absolute best match. It guarantees the most accurate result. The problem: it's incredibly power hungry. On the other hand, you've got fast search algorithms. They're way quicker because they only check a handful of likely spots. But the trade-off is they might accidentally miss the real best match.
So the real puzzle for engineers is this: how do you get that lightning speed of a fast search without giving up all the accuracy? And to make things even harder, what happens if the lighting changes? A cloud passes overhead and suddenly all the pixel values change, which could totally confuse the algorithm, even if nothing has moved at all.
And here is the really clever solution. Instead of trying to match the raw pixel colors, a lot of modern algorithms match something much more stable: the edges. Just look at the difference here. The edges in image B capture the core structure of the person's face and hat, and those lines are way less likely to change if the lights in the room get a little brighter or dimmer. And this quote just nails it. The edges have the most robust, the most stable information in an image. So by focusing on matching these structural features, instead of fickle, changing pixel values, these algorithms can be both way faster and a whole lot more reliable. It's a win-win. So we've gone from a simple illusion to a complex system that lets machines turn motion into data they can track and even start to predict. This is the foundation for tech that is already changing our world. Which leads to one last pretty fascinating question. Once a machine can perfectly predict the simple motion of a car or a person, what will it be able to predict next? The journey from seeing motion to understanding intention, well, it might be shorter than any of us think.